Hi everyone, I'm Eric, and today we'll be continuing Taylor number theory. Yes, again. And today we'll be considering congruences. Now, in order to consider congruences, we first have to introduce quite a few new stuff. So first is this mod thing. Now, I'm pretty sure you guys probably saw it in my earlier videos, and I've also said what mod is, but in this video, I'll specifically say what mod is. Mod is basically when you find the remainder of a division equation. So, for example, it's 5 mod 7. And in code languages, we write it as percentage mark. And in real life we don't, so I'm just going to write it as percentage mark. So it's 5 mod 7 is basically you write a division equation. It's 7 over 5, that's for sure. Now it is also 0 with a remainder of 5, and what mod does is it finds this remainder 5. And then there is this congruence thing. And this is 3 noodles lying on the ground. What are they doing? Get up and walk away. Well, this looks like an equation mark, and it have a very big relationship to equations and also mod. So for example, 5 mod 7 is 5. That's of course. That's obvious. And 12 mod 7 is also 5, since it's 1 times 7, and 7 plus 5 is 12. So we say that 5 and 12 modulo 7, rather as MOD, 3 letters for short. We say that 5 is congruent to 5 is congruent to 12 modulo 7. And we write it with the 3 noodles lying on the ground, which is basically an equation mark with the addition of another line, which you can think of it as the line of the division, and both of these dots get covered up. That's an easy way of understanding it. And now we finally get to the first sentence of the PowerPoint of the PPT. So if M divides A minus B, we say that A is congruent to B modulo M. Why? If we only know M divides A minus B, then we can already say that A is congruent to B modulo M. We write it as this, and it's at the start of the PPT this whole time. So now, you guys probably already know why this is true, but I'll prove it using an algorithm, so it's more obvious. So A is it can always be represented as nm plus x, where n and x are positive integers. So for example, 11 is 2 times 5 plus 1. In this case, n is 2 and x is 1. So A can always be represented as this. And since we know that M divides A minus B, then A minus B must be a multiple of M. And we're going to write this as this, where y is also a positive integer. And now if we add both sides by b and and subtract both sides by my, then we have b equals a minus my. And right now we know what a is. It's nm. So it's basically b is nm plus x minus. Now I won't write it as my, since it will confuse and not let people notice these two same m's. So I'll write it as ym, so it will be pretty obvious why we can write it as n minus y times m plus x. And we noticed that the x hadn't changed throughout the process. And why is that? That is because of this factor. And a seemingly useless statement as this actually saves the day. So we already know that a minus b is a multiple of m. And then a can also be represented as a multiple of m plus a random integer. Now when these two multiples of m meet, they can have their own private space for argument and leave the x alone. And that is why the x is protected and untouched throughout this process. Now, we will come to a quite obvious statement right here. So it says that if a divided by m leaves the remainder of r, then a is congruent to r modulo m. And you guys probably already know why that is true, very true. And the remainder satisfies this, since the remainder cannot be greater than m. And so, every integer is congruent modulo m to a number between m and m minus 1. And this random Chinese character has come the wrong way, I guess. Wrong stage. Bye-bye. It's not your place. Okay, now it's gone. So this is probably already obvious to you why, and I'll just give you guys an example. So let's say, what about 13 and 6? Okay, 13 and 6. 13 modulo 6 is, we're going to write it as percentage mark yet again. 13 modulo 6 is 1, and 1 is between 0 and 5. So that is one teeny example to you. And now we have come to a not quite obvious thing, but it will be obvious if you actually think about it. So if a1 and b1 modulo is congruent modulo, if a1 is congruent to b modulo m, and a2 is congruent to b2 modulo m, then we can say that a1 plus or minus a2 is congruent to b1 plus or minus b2 modulo m. And notice that you can only it can be only plus on both sides or minus on both sides. It can't be 1 plus and 1 minus, because it might work if you are too lucky, but it won't work if you aren't. So you can also use multiplication, but not division. Division won't always work. So for example, 15 times 2 is congruent to 20 times 2 modulo 10. But we will come to a disaster if we say that 15 is congruent to 20 modulo m, won't we? Modulo 10, because that's obviously incorrect. So division causes quite a bit of problems, and it is a bit of a troublemaker. So we can't always use division. However, if the element we want to divide is relatively prime to this m, then we can do it. So for example, let's say 2 times 7 is the same as is congruent to 12 times 7 modulo 10. And now we can divide 7. And we have 2 is congruent to 12 modulo 10, and then we won't come to a disaster. And let's go to the next slide, which is examples. Now these examples are quite easy, and we'll skip to your algorithm later on. So first we see this plus 12, and it is disturbing us. I mean, if we leave the x alone, then it will be much easier for us, won't we? So if we subtract 12 from both sides, we have x is congruent to -7 modulo 8. Whoa, we come to a negative number. How cool. We don't want that, so let's add 8. Why? -7 plus 8 is 8. What great news. I'm obsessed with 8 today. And we had come to this. So it would be surprising to know that -7 modulo 8 is actually 1. And it is quite a bit confusing. So we'll just leave the positive integers and we'll just leave the negatives on their own because we do not want them to be a troublemaker. And also this thing, 4x is congruent to 3 modulo 19. We can always just try every single possible x. But there's an easier way to do this. So we'll multiply both sides by 5 and we have 20x is the same, is congruent to 15 modulo 19. Now it won't seem any more helpful than this, but in fact it is much more helpful since we know that 20 over 12. We know that 20 modulo 19 is 1, and if we multiply both sides of that equation by x, we get is 20x is the same is congruent to x modulo 19, and we had actually solved this because if we just substitute this x, and thus we have x is congruent to 15 modulo 19. And we're done. Lastly, this thing. Now it makes a headache, really. So we'll get our last resort, which is to try out every single x possible, and that is from 0 to 6, or else it will count as the same solution. Now, big spoiler, x only works when it's 2 and 3.